Hi there, my name is Batyr, and I'm a master's student working with Nadi at the University of Alberta. I'll be talking about our industry collaboration experience with IBM Canada, particularly about the challenges of implementing software variability in a large-scale open-source system known as Eclipse OMR. Eclipse OMR is a set of reusable C++ components for building language runtimes. OMR doesn't stand for anything, but previously it stood for Open Managed Runtimes. OMR can be used to build a runtime environment for a variety of languages, such as Java as shown below. OMR is actually being used by OpenJ9, which is a popular Java virtual machine. In the same manner, since OMR components are reusable and language agnostic, you could use Eclipse OMR to build a runtime for your own language. OMR provides a variability across languages and architectures, and to manage this variability, OMR has a non-standard variability implementation mechanism known as static polymorphism. The motivation behind it is that OMR developers want to have all variability types resolved at compile time. And to achieve that, OMR developers use a combination of known techniques plus their own developed workarounds. I won't go into the detail for the sake of time, but the details are in the paper. These techniques help Eclipse OMR developers delegate more work onto compile time. Because remember, OMR is used for building runtimes, and therefore, high runtime performance is crucial. At the beginning of our collaboration in 2017, we thought that static polymorphism is the main problem causing the code base to be convoluted and hard to understand. We investigated performance impact of switching to the more typical dynamic polymorphism with the motivation that it may alleviate some of the complexity problems, while our previous work focused on the trade-offs between static and dynamic polymorphism, we realized that there are still open problems that require more reengineering effort. So it took us some time to realize that a bigger picture variability is needed to understand what problems developers experience. To get the big picture, we interviewed 6 developers who contributed to OMR or worked with products that use OMR, such as OpenJ9. After synthesizing our results, we prepared a presentation to share with the entire Eclipse OMR team. There were 15 participants in this meeting, several of whom were not part of our interviews or any previous discussions, which allowed us to get additional validation on the synthesized results. Based on the interviews and discussions with the team, we identified 8 challenges and 3 constraints. All of the challenges and constraints are described in detail in our paper. One of the challenges, for example, is missing extension mechanisms for enumerations and unions in C++. In other words, C++ doesn't provide a way to extend enumerations or unions the same way we would extend classes. One of the examples of constraints is the C++ version. OMR developers, for example, cannot use C++ 17 features because the newer features of the language are not yet supported on all architectures that OMR supports. Therefore, they always stick to the lowest common denominator of C++ that's supported on all architectures. So our goal was to try to redesign the system to overcome these challenges. And while we turned to the literature for variability implementation strategies, we quickly realized that most of these require a large rehaul of the system or don't address all the challenges. So instead, we decided to tackle problems in an incremental manner. Take one problem and propose a solution to it. So we agreed to start with the C++ enumeration problem that I mentioned earlier. In the compiler component of OMR, opcodes are used to specify some instruction to perform at runtime. For example, iconst on the left loads a 32-bit integer constant. Additionally, each opcode has a list of properties such as name and token used internally in the codebase. The file on the left contains a snippet of several values of an opcode enumeration in Eclipse OMR. The file on the right contains a list of properties of opcodes defined elsewhere in the codebase. So the first thing to notice here is that all the relevant information about opcodes is not centralized, and that forces OMR developers to manually keep track of the order of the opcode information among these files. For example, the first element on the left should always correspond to the first array entry on the right. And the second element on the left should correspond to the second array entry on the right. And there are many spread out header files like that, referring to the same set of opcodes. This approach with multiple files spread out on the code base is error prone in a sense that if you accidentally swap the two values on the left, the two values or the array entries on the right will have their properties incorrectly assigned to each other. Thus, OMR developers have to manually keep track of the order among these files and be careful adding or modifying any opcodes. This is a comment from one of such files. In the previous example, we just saw 2 files, but in reality, there are 12 files that have to be modified in order to add or change properties of some opcodes. After better understanding the enum extensibility problem, we looked at similar open source software solutions. We selected 3 candidates for the problem. The first one is a custom domain-specific language, or DSL, for managing Eclipse OMR opcodes. This solution is inspired by LLVM TableGen, which is a DSL that's used to describe architecture-specific information. This solution would be best for OMR, but it would take time to add the support for the DSL and force the developers to learn a new language just to manage the opcodes. So the second option was to use Python scripts that would read some JSON file with all opcodes information stored in it and automatically generate C++ header files. That way, there is no need to manually keep track of the order of the opcodes anymore. However, OMR developers did not want to add unnecessary Python dependencies to keep the system as minimal as possible. The third candidate is the C++ macro-based solution, inspired by how Mozilla's JavaScript engine, called SpiderMonkey, manages its opcodes. After discussions with the team, this solution seemed to be the most preferred one due to its simplicity and minimalism. Our macro-based solution was implemented and merged into the main branch after continuous discussions and code reviews with team members. We centralized all spread out data about 735 opcodes from 12 header files in a single file that's now easy to inspect and maintain. Now, order consistency among opcodes is automatically enforced. Since 2017, we've learned several lessons and tips that might be useful for other industry research collaborations. Understand the bigger picture. It took us a while to realize that switching from static to dynamic polymorphism will not fix all the problems. We conducted the interview study and had a bigger conversation with the whole team to get the big picture of challenges and constraints in Eclipse OMR. Do not underestimate practical constraints. As researchers, we thought that latest and greatest would be the most welcome option for the various requirements. However, the interviews and discussions with the team revealed that things like the C++ version are practical constraints that may easily rule out such options. Identify feasible changes. We realized that any complete rehaul of the system to use coarse-grained variability implementation strategies requires deep knowledge of the codebase and impossible to do without direct involvement of the team members. We found that from our research team side, incremental changes with continuous code review feedback was more feasible. In summary, we talked about the variability implementation mechanism in Eclipse OMR. We also discussed the identified challenges and constraints we synthesized from the interviews and discussions. We also talked about 3 potential solutions for one of the challenges, one of which we implemented and merged into the main branch of the project. And finally, we share our lessons learned and tips that might be useful for other industry research collaborations. That's it from my side. Let me know if you have any questions, and thank you.
All right, so welcome back. I am here with the first 2 authors of the paper, Batyr and Sarah Nadi from the University of Alberta. So do add questions to the chat. So I have a question. I work in requirements engineering as well as software product lines, and some aspects of your interview study strikes me as like a really comprehensive requirements elicitation exercise. So, you know, how does my intuition fare with that description?
Yeah, so initially, we wanted to kind of, what was the purpose of the interview study? It was to try to understand the challenges and the constraints within OMR, and that of course relates to requirements, right? Because
yeah, stakeholders and requirements, right? And yeah, constraints. Yeah, so it is an interesting exercise.
Yeah, because some requirements cannot be implemented due to some constraints, like the one we had with C++ version. They cannot choose anything like C++ 17 because it's not supported yet, like on some of the platforms, such as far as I remember, IBM AIX. So yeah.
Yeah, and I think another thing even is that it was almost like the requirements weren't gathered at the start, because this, like a lot of the re-engineering that happened, because it was initially closed source, then it changed to open source, and it was almost like on the fly kind of thing. So I think some of what we found is kind of in retrospect requirements, that it was, very Java oriented, but now you need to support other languages, and that wasn't kind of taken into account internally in the code, even like kind of the naming and things that are inside. So yes, I think there's a lot of requirements gathering that we had to do, but we couldn't satisfy all of them. But yeah.
Right. So you picked one. Are there plans to address the others? Like, are the others, like have you mapped out a nice research program for the next couple of years? Part of this process, or are some of them just like incredibly almost impossible, like because of the constraints?
So, but do you want to take a stab and then I can?
Sure, yeah. Yeah, you're right. Actually, some of them are quite hard to do it on our own as researchers. And it was kind of, even with this problem that we chose, we needed to go back and forth with the team members just to make sure we're on the same track. In terms of other solutions, like maybe making a large scale refactoring onto feature-oriented sort of product lines, it will take, like, it requires a deep knowledge of the code base. So at the current time, as far as I know, we are not doing any kind of, we will not be doing any challenges, like we'll not be proposing any solution. But yeah, maybe Sarah can add.
You won't, you're graduating.
Yes, that's one, yes.
Yeah, so actually this is, yeah. So that this is actually, this marks like, this was a 3-year collaboration with IBM, and this is kind of marks the end of it. Because I think what we did was kind of went backward. We thought there was one problem that we started tackling and kind of changing things, but then we're like, okay, this doesn't help with the main issues. So we kind of stepped back and did this interview study and tried to get a bigger picture. So what's useful about this, what they found useful, is that at least it explicitly marks for them, what are the perceptions of the code, people interacting with it, and so on. So we're not gonna, we don't have plans ourselves to change this, but I think internally they will, because something like the Java legacy we found, that really requires them to think about what kind of opcodes they want to offer, what kind of the different languages. So I think it was an eye opener for them, and they have plans to kind of change that. But for us, it marks kind of the end of figuring out this gigantic project and figuring out all the variability inside it.
So you've got a nice, I mean, your solution, is sort of this, an adaptation of existing solutions. And do you see, does it suggest kind of a possible way of devising almost a collection of build patterns, right? So like one of the related approaches is collection of design patterns, code patterns. But do you imagine that there might be a collection of build patterns that could support some of these extensions and variabilities?
Probably, I would say that, because we adapted the solution from already existing just-in-time compiler. Yeah, but OMR itself is different because it's not a just-in-time compiler on its own. It's more like disconnect the components that you have to bring in together, add some adapter code, for example, and make it work on your own. But it's not like a standalone just-in-time compiler. So in some parts, yeah, we would, for example, if you decide to take a look at SpiderMonkey and see what other patterns you can reuse in OMR, you can do that. But there'll be differences that you need to take into account. So because of the nature of the system.
Yeah, I was just gonna add, I think, I mean, I think it is a recurrent pattern in the sense that the language itself does not support this, right? So C++, you cannot like extend enumerations like you do with classes. So it could be kind of, like if this is your problem, here's a pattern. I'm not sure if we call it a build pattern, design pattern, whatever it is that can be used. And we were quite surprised that this was the solution they went for, because like Batyr, we looked first into like LLVM and the it was LLVM, right? Like the DSL they use. Yeah, and we thought that's what they'd go for, but so
that's interesting. So and if you had to do it all again, like if you, knowing what you know now, 3 years ago, would you do things differently? Would you do anything differently?
It's a good question.
I can take a stab if you want.
Sure. Well, take some time.
Yeah. Well, also Batyr like joined the project in the last like year and a half, so he wasn't there from the beginning.
Okay.
So I would definitely reverse things to start with the interview study. Like we talk to a lot of like, I mean, basically our direct collaborators, right? But honestly, I don't think I understood kind of the big picture of everything till 2 years into the project. It's very hard, like understanding code that you did not write, where like it's also like different kinds of patched up solutions. So I think spending more time upfront to kind of really identify the pain points rather than trust what they tell you or like what they perceive as the pain points, and it's also like one point of view. I think kind of, in retrospect, that would have helped. And then maybe we could have been able to solve more of the challenges. Because in the end, what we thought the whole like static versus dynamic polymorphism is the problem with readability. And I don't think that was the only thing. I think it goes down to more deep like design considerations to make this really configurable and extensible and so on. And so, I think they're already changing. They changed something. Okay. I can't remember what it was. Like even since we wrote this, they've already changed something. So
that doesn't surprise me at all, right? Like I know that you solved one of their challenges, but I think that the identification of the other challenges, like you say, it does tell them a lot about their own code, right? And identifies the struggles that people are having with their code, and it doesn't surprise me at all that they might be looking for workarounds or solutions to some of those. Yeah, that's a hugely valuable to them. So any last takeaways that you would like people to have?
I just say come in with like more open perspective. Than I think I was like, oh, I know the latest and greatest of all the product line research, and let's try to apply it. And I don't think that was very successful. So just listen and try to figure out what really is needed in the project.
Awesome. Well, that ends the session. Carry on in the discussion room.